So this will be the 5th lecture out of chapter 5 or chapter 3, and this will be the final lecture. So in this lecture, we're just going to take another stoichiometry problem, and in this case with a limiting reagent, and work through that one so that you can see how that is done. Okay, so if we take this reaction, so iron 3 oxide, so if we take 12.5 grams of it, and 10.3 grams of carbon monoxide and react them with each other to make iron and carbon dioxide, then how much iron could be produced? Okay, so to work this problem, so first of all, you would want to make sure that the equation is balanced. So I may give it to you balanced to save some time, or I may expect you to balance the chemical equation, but that's the first thing you always have to do is make sure it's balanced. So we got 2 irons on the left and we got 2 irons on the right. So iron is balanced. We have 3 carbons on the left and 3 carbons on the right. So carbon is balanced. And then we have 3 oxygens here and then another 3 oxygens here. So we got 6 oxygens on the left and we got 6 oxygens on the right, because you would take the 3 times 2. So the equation is balanced. Okay, so that is done. So now what you have to do is you have to determine what the limiting reagent is. Because I may not have given you, or you may not have started this reaction with exactly the right amount of each of the 2 reagents. So you had to just figure out, do you have the exact right amount of both or not? And if you don't, then you're going to run out of one of them before you run out of the other one, and the one that you run out of first is going to be the limiting reagent, and that's going to be the one that determines how much product you can make. Okay, so there are several ways to determine the limiting reagent, and we're going to look at 2 different ways. So method 1. So what we're going to do is determine how much product we can make from either of the reagents. In this case, there's only 2 reagents, but you could have reactions with more than 2 reagents. So we're simply going to determine how much product we can make from each reagent. And the reagent that can make the least amount of product is going to be the limiting reagent. So we want to see, we could look at how much iron you can make, or we could look at how much carbon dioxide you can make. It doesn't matter. We're just going to take one of them and figure out how much we could make from both of these 2 starting materials. Okay, so to do that, you need molar masses, because I gave you grams to start with, and you have to convert to moles is the first thing. After you balance the equation, the first thing you have to do is convert grams to moles. And to do that, you need molar masses. So I've calculated the molar masses for you here. So take the periodic table entries for iron, carbon, and oxygen, and calculate your molar masses. So 28.01 grams per mole for carbon monoxide. Iron 3 oxides, 159.69 grams per mole, and this is iron solid, so that's just elemental iron, so that's you just look on the periodic table for it. So 55.847 grams per mole for elemental iron. Okay, so now we can do the math and figure out this problem. Okay, so we want to convert grams to moles. So what I'm going to do is I'm going to do all of this in one-dimensional analysis. You don't have to do it. You can break it apart into pieces, but I'm going to show you how to do it all at once. So we're going to go from grams of this to grams of that in one sequence of calculations. And then we're going to go from grams of this to grams of that, and to grams of iron, and see which one produces the least amount of iron. Okay, so first thing we're going to do is take this 12.5 grams of iron 3 oxide and convert it to moles. So we're going to use the molar mass to do that, right? So since grams are on top here, we need grams on bottom here. So we need the 159.69 grams of Fe2O3 on bottom, and then we need the 1 mole of Fe2O3 on top. Okay, so now grams of Fe2O3 will cancel out, and now we have moles of Fe2O3, so now I'm going to convert to from moles of Fe2O3 to moles of iron. And to do that, that's when we use the molar ratios, 1 to 2. So we're going to make, so since moles of Fe2O3 is on the top here, we need it on the bottom here. So 1 mole of Fe2O3, right? The number here is the number here, the coefficient in front of it in the chemical equation. And then that's gonna convert to 2 moles of iron, which is, we're using the number in the chemical equation for that. Okay, so now moles of Fe2O3 cancel out. And sorry, there should be 2 moles of Fe. And now I want to convert that to grams. To convert that to grams, then I go to the molar mass of iron. So since I have moles on top, I need moles on bottom. So 1 mole of iron is 55.847 grams. And if you calculate that out, you should get 8.77 grams of iron could be formed there. Did I do that right? Yes. Okay, so now if we do the same, sorry, need the calculator. For the 10.3 grams of carbon monoxide. So let's see how much iron you could make from 10.3 grams of carbon monoxide. So first we're going to convert grams to moles. So that's again where we use the molar mass at. So 28.01 grams per mole. So since grams is on top, we need grams on bottom here, 28.01, right? Grams of CO per 1 mole of CO. So then grams of carbon monoxide cancel. Now we have moles of carbon monoxide. Now we're going to convert to moles of iron. To do that, we use the molar ratio. So it's a 3:2 ratio. So 2 moles of iron per every 3 moles of carbon monoxide. And then moles of carbon monoxide cancel out, so now we're in moles of iron, and now we need to convert that to grams. So 55.847 grams of iron in every 1 mole of iron. And then moles cancel, and we're left in grams. So 10.3 divided by 28.01 times 2 divided by 3 times 55.847 would be 13.69. Okay, so using 12.5 grams of iron 3 oxide, you could make 8.7 grams of iron. Using 10.3 grams of carbon monoxide, you can make 13.69 grams of iron, and you go with the one that is smaller. You can only make, in this case, you're gonna, as soon as you make 8.77 grams of iron, there is no more iron 3 oxide, so the reaction stops at that point. So you cannot make 13.69 grams of iron. So that basically means the iron 3 oxide is the limiting reagent. So that is the maximum amount of iron that you could make from these quantities of starting materials. Okay, so Fe2O3 is the limiting reagent. Okay, so that's one method to determine limiting reagent. The other method is, given the amount of one starting material, calculate how much of the other you need. So if we started with 12.5 grams of iron 3 oxide, how much carbon monoxide would you need to do this reaction? So to do that, we're going to convert to moles of iron 3 oxide, and then we're going to convert to moles of carbon monoxide, and then we're going to convert to grams of carbon monoxide, right? Okay, so to convert to moles, we just need the molar mass, so 159.69. So grams cancel out, and now you're in moles of iron 3 oxide. Now we're going to convert to moles of carbon monoxide. How do you do that? You use the molar ratio, right? It's on a 3:1 ratio. So every 1 mole of iron 3 oxide needs 3 moles of carbon monoxide. So since so the grams canceled out, so we're in moles of Fe2O3. So we need the moles of Fe2O3 on bottom. right? That's from the chemical equation using that coefficient of 1, and then 3 moles of carbon monoxide on top. So now moles of Fe2CO3 cancel out, and we have moles of carbon monoxide, so we can convert that to gram using the molar mass of carbon monoxide, which we said was 28.01. Right, so moles of carbon monoxide cancel, and now you're in grams of carbon monoxide. So that would give you 6.58 grams of carbon monoxide is needed for 12.5 grams of iron 3 oxide. So now you compare what you need to what you have, and what you have is 10.3 grams is what you have. So you need less carbon monoxide than you have. That means carbon monoxide is in excess. That means iron 3 oxide must be the limiting reagent. Okay, so since 6.58 grams is needed, but you had 10.3 grams, CO is in excess, and Fe2O3 then is the limiting reagent. So either way allows you to figure out the limiting reagent. Okay, so we've answered question 1, and in the process of doing all of this, we answered question 1, which was starting with this amount of iron 3 oxide and carbon monoxide, how much iron can you make? Well, we just calculated that right here. Right, that is the maximum amount that you can make, 8.77 grams. So that's your theoretical yield of iron. Okay, so now if I gave you this question then, so let's say the reaction actually only made 7.66 grams, what is your percent yield? So you would just take the 7.66 grams of iron, that's actual, and divide it by the 8.77 grams of iron, which is theoretical, times 100%. And your yield would be 87.3%, right? Okay, so then I could ask you another question now. So since the reaction was not 100% yield, and if there's no side products, then that must mean there's starting material left over. So how much iron 3 oxide and how much carbon monoxide is still left in the flask at the end of this reaction? So one of these is easier to calculate than the other, and the one that's easier to calculate is the one that's the limiting reagent, because the percent yield is based on the limiting reagent. So for Fe2O3 then, since that's the limiting reagent, this is an easy calculation. So we can take your 87.3% yield, divide that by 100 to get back to a fraction, to get back to decimal. So that's 0.873 is the fraction that reacted, or 100% minus 87.3% is 12.7%, is how much did not react. Or the fraction is 0.127. Okay, so we started with 12.5 grams of Fe2O3. If we multiply that by the 0.873, then that tells you that 10.9 grams of Fe2O3 reacted. Or if we take the 12.5 and multiply it by the 0.127, then that tells you that 1.59 grams of iron 3 oxide did not react and is still in the flask. Okay, so figuring out how much carbon monoxide is left unreacted is a little bit harder since it was in excess to begin with. So there's a few extra steps to do to figure that out. So earlier we calculated how much CO is needed to react with 12.5 grams, right? We went through this dimensional analysis to figure out that you need 6.58 grams of carbon monoxide. Right, that was the method 2 that we used to figure out which was the limiting reagent. So this calculation is needed to figure this out. Okay, so you needed 6.58 grams of carbon monoxide. And you had 10.3 grams to start with, right? So, but you only needed 6.58 grams, so if we just subtract the 2, then you had this, but you only needed this, to react with all of the iron 3 oxides. So there was 3.72 grams of carbon monoxide that were never going to react to begin with, because as soon as the 12.5 grams of Fe2O3 is gone, the reaction's done. And at that point, you've only consumed 6.58 grams of carbon monoxide, so 3.72 grams is in excess to begin with. So what we want to do now is use that 6.58 grams of CO that could have reacted if all of the Fe2O3 reacted. But it did not. It was only 87.3% yield. So it did not all react. So we can take that 6.58 grams that could have reacted and multiply by the 0.873, and that would give you 5.74 grams of CO actually reacted. Or 6.58 grams that could have reacted times the 0.127 gives you 0.836 grams did not react out of the portion that could have reacted. So hopefully that's all making sense so far. Okay, so now let's just take these two numbers and add them together. So this, that was 3.72, that was never going to react because it was in excess, plus the 0.836 that did not react but could have reacted, and that gives you 4.56 grams of carbon monoxide is left in the flask unreacted. Or there's another way to get that number. So we started with the 10.3 grams of carbon monoxide, right? That's how much we put into the reaction. And we calculated right here that 5.74 grams actually reacted. So if we just subtract what we started with and subtract what actually reacted, then we get 4.56 grams of carbon monoxide is left unreacted, right? So that's how you figure out how much unreacted starting material is left over if it was not the limiting reagent. Okay, so let's take one more problem. So let's take this problem. So in this case, three things react. Three reagents: ammonia, NH3, oxygen O2 gas, plus a methane CH4 gas, platinum. So if it's wrote on top of the arrow, that typically means it's a catalyst. So that's just there to speed the reaction up. So then it makes HCN gas and water. So if we start with 11.5 grams of ammonia, 12 grams of oxygen gas, and 10.5 grams of CH4 gas, what's the limiting reagent? So it may be that these are the exact right amounts of everything, or it may be that it's not. And so you have to figure that out. If this is not the exact right amount of everything, then you need to figure out what's the limiting reagent, because how much HCN is produced, the next question is going to be dependent on the limiting reagent. Okay, so how are you going to do this? So first of all, we should check the equation is balanced, and it is a balanced chemical equation. So then the next thing you would need to do is you're going to have to convert grams to moles. If you want to convert grams to moles, then you need molar masses. So you would have to calculate the molar masses of everything. You don't need to calculate the molar mass of water because the question didn't ask anything about water. So if you calculated the molar mass of water, you're just wasting your time on a problem like this. Okay, so the question obviously involves ammonia, oxygen, methane, so we got to calculate their molar masses, and the question asked about how much HCN would be produced, so we had to calculate its molar mass as well. So I've done that for you here, calculated the 4 molar masses that you'll need for this problem. So now let's convert each of these grams to moles. And so what I'm going to do is I'm going to go ahead and do the full conversion, go from grams of this to grams of that, and grams of this to grams of that, and grams of this to grams of that. And whichever one produces the least amount of HCN, that's the limiting reagent, and that's the maximum amount of HCN that you can produce. Okay, so if we do that, so 11.5 grams of ammonia, so let's convert it to moles. So 1 mole of NH3, 17.03 grams of NH3. So that's where we use the molar mass. And then now we're going to convert to moles of HCN. So this would be, we reuse the molar ratio from the equation. So 2 moles of ammonia makes 2 moles of HCN, so it's a 1-to-1 ratio. So since moles of ammonia is on the top, we need to put the, right here it's on the top, so now we need to put it on the bottom here. And now we're going to convert to grams of HCN. So we need the molar mass. Okay, so we have moles of HCN on the top already, so we need the moles of HCN on the bottom. And then 27.03 grams of HCN, so we need the molar mass of HCN. And if you do that calculation, you should get 18.3 grams of HCN could be produced from 11.5 grams of ammonia. And now we need to do the same thing, starting from oxygen or starting from CH4. So let's just take this. We'll just copy that because all of these calculations are the same, and paste it. And then let's just change some things. So now we're starting with 12 grams of oxygen instead. Okay, so this is going to be 12 grams of O2. So we need the molar mass of O2. So 1 mole of O2 is 32 grams of O2. And the molar ratio is 3 to 2. So 2 moles of HCN on top. So we don't have to change the top there. We just have to change the bottom here. So that would be 3 moles of O2. Right, so we put the number in front of O2 in the chemical equation there. And then the last column stays the same because, so let's see, this is going to, grams of O2 is going to cancel, moles of O2s are going to cancel, moles of HCN are going to cancel, and we're left in grams of HCN. So if you do that calculation, then this would give you 6.76 grams of HCN. So you can already see that that's smaller than the 18.3 that we calculated above, so ammonia NH3 is in excess. So now it's down between O2 and CH4. So let's do the same thing for CH4. Okay, so we're gonna, this is gonna have to be CH4. That's gonna have to be CH4. CH4 there, and the molar ratios will change, and all of that stay, and this will change. Okay, so HCN, so how much of that did we start with? 10.5 grams. So 1 mole of HCN, so we need the molar mass is, no, not HCN, CH4, sorry. Right, 10.5 grams of CH4, and its molar mass is 16.04. And this is CH4. Right, so grams of CH4 will cancel. Now we're in moles of CH4, so now we need the molar ratio between CH4 and HCN, and it's a 2 to 2 ratio, or 1 to 1. So 2 moles of HCN, 2 moles of CH4. And okay, so what cancels? So grams of CH4 cancel, moles of CH4 cancel, moles of HCN cancel, and now we have grams of HCN, which would be 17.7 grams of HCN. Okay, so that's the smallest. So that is your maximum yield of HCN, 6.76 grams, which means that is your limiting reagent. All right, so your limiting reagent in this problem is the 12 grams of O2. and the maximum yield is 6.76 grams. Okay, and that's it. We answered the 2 questions that we set out to answer. Okay, so hopefully that made sense.